This video is part 1 in a series about using simple continued fractions to find solutions to Pell's equation. We'll set up the problem and then examine some convergence of the square root of d, a term in Pell's equation. As we will see, the convergence contains solutions to Pell's equation. Let's get started. We are given d, a positive integer that is not square. What we want to find is two integers x and y that satisfy x squared minus d times y squared equals 1. This is Pell's equation. We are seeking integer solutions, making Pell's equation a Diophantine equation. That's our problem statement. Now let's look at some convergence of the square roots of some numbers that could be d. We'll do two cases. In the first one, d equals 7. The simple continued fraction of the square root is 2, 1, 1, 1, 4, with all but the 2 repeating. There are 1, 2, 3, 4 terms in the repeating part, so the period is 4. Here's a table like we use, as usual, to calculate convergence. We have a row for the subscript k, a row for a, the terms of the simple continued fraction, and p and q, the numerator and denominator of the convergence. We have a couple of other rows too. We'll get to those soon. We'll fill in the first two rows. We're looking at the first period for now. K goes from 0 up to 4, and these are the terms of the simple continued fraction. The next row has what I'll call structure. It just indicates where we are in the predictable structure of the simple continued fraction. This term is the non-repeating term a0. These terms form a palindrome, and this term is twice a0. Twice this term equals this one. Please see this other video about the pattern that emerges in the simple continued fractions for square roots. Here are the convergence through the first period. Please see this other video about calculating convergence if you'd like to see the process. In the bottom row, what we will enter is p squared minus d times q squared. Here are the values. Let's talk through one. In this column, p is 2 and q is 1. Also, d is 7, so p squared minus d times q squared equals 2 squared minus 7 times 1 squared equals 4 minus 7 equals negative 3. That's where this negative 3 came from. What we really need to notice in this row, though, is this 1. When a 1 appears, it means that p and q provide a solution to Pell's equation. Pell's equation is x squared minus d times y squared equals 1. If x equals p equals 8 and y equals q equals 3, with d equals 7 we have 8 squared minus 7 times 3 squared equals 64 minus 63 equals 1. Let's look at the information for another period. Here it is. Once again we have a 1, so we have another solution to Pell's equation. If x equals p equals 127 and y equals q equals 48, then p squared minus 7 times q squared equals 16,129 minus 7 times 2,304 equals 1. Let's look at the next period. I didn't write in all the values of p and q just to save a little space. The values that matter are filled in. We have a 1, and therefore this p and q provide another solution to Pell's equation. Maybe you're ready to make a theory about how this works, or at least guess what you'll see if we do another period. What do you think? Will there be another solution to Pell's equation? In which column? And where in the structure is the solution? Here's the next period. There's a 1 here, so this p and q provide a solution to Pell's equation with d equals 7. We've done 4 periods now, and we have a solution in each of these columns where a 1 appears. If we kept going and looking at more and more periods, we keep getting a solution in each period. That wraps up the discussion about the first case. Let's look at the second case. This time d equals 41. The square root of d is 6, 2, 2, 12, with the 2, 2, 12 repeating. There are 1, 2, 3 terms that repeat, so the period is 3. Here is the table with the same rows. This time in the bottom row we put the value of d. It's p squared minus 41q squared. We have enough columns to get through the first period. We'll fill in the first 2 rows. The values of a are from the simple continued fraction. Here's the next row indicating where each term is within the structure. This is a0, and then the 2 2's make the palindrome, and then twice a0. And here are the convergence. Do you think we will have any solutions to Pell's equation with d equals 41? Can you get out a calculator and figure it out yourself? Here's the bottom row. This time we do not have a solution. We have a negative 1 here, but what we would need is a positive 1. So none of these pairs of p and q provide a solution. Now what do you think? Will we have solutions? Here is the next period. Positive 1 appears here. P equals 2049 and Q equals 320 provide us with a solution to Pell's equation with d equals 41. Here is the next period. Once again, we have a negative 1, but not a positive 1, so we don't have any solutions in this period. And here's the next period. This time there is a 1. This p and q provide a solution to Pell's equation with d equals 41. If we kept going and going, we'd have a solution in every other period like this. Do you have a theory for how this works now? In part 2, we'll outline the process and work examples. In this video, we wrote our problem statement for Pell's equation and examined convergence for the square roots of some numbers that could be d. That's all for now.